Okay, this video is on sections 1.8 and 1.2. They are both talking about doing hypothesis testing and confidence intervals with two means. And there's a difference between independent and dependent samples, which we will discuss in these sections. So the difference between the two sections, 8.1 and 8.2, are the same two differences that you've experienced in, principles of statistics or statistics 1, between sigma known and sigma unknown in the world of the means. So recall that when sigma, the population standard deviation, is known, then you can use a z-test statistic. Typically, we're looking for the sample size to be 30 or larger. If it's smaller than 30, then we need to know that the data came from a normally distributed population. 8.2 deals with a sigma unknown, so the population standard deviation is not available, and therefore all we have is the less accurate sample standard deviation. And if the sample size is fairly large, like 30 or more, technically you can still use a z-test statistic. But if the sample size is small with a normally distributed population and we have no sigma, then we will be forced to use a t-test statistic. So besides those two differences that you should be fairly familiar with from Stats 1, what we're really exploring here is hypothesis testing with two populations, and that's much more common in testing. So we've so far worked with one set of data, testing about oil times and how fast it is to change the oil. So you focus on one company and collect a bunch of oil times, or we've focused on a particular manufacturer and how long their light bulbs last. So we would take a sample of light bulbs from that one particular manufacturer and test whether their claim on how long they last is true or not. But in many studies, we are comparing two different population sets, for example, men versus women, or one shoe brand versus another shoe brand. So when comparing two parameters from two populations, there are two different ways that the samples can be collected. You have independent samples. Independent samples are selected from one population, and it's not related to the sample selected from the second population. So if we were to, for example, try to test the sales in two different bars. So a sample of days randomly selected from bar number 1 and a sample of days randomly selected from bar number 2. They are completely disjointed or independent samples. Dependent samples, also called a matched pairs design or paired samples, is when each member of the sample corresponds to a member of the other sample. So there are cases where dependent samples are literally the same people. For example, if I was trying to compare running shoes to different brands, it would make more sense to create a dependent sample and put one shoe brand on one foot of a subject and the other shoe brand on their other foot, and therefore being able to directly compare the two shoes to the one runner. So there are definitely situations where dependent samples are is the most effective way to go about the study, and in other cases the samples are not related in such a way. So here's a little diagram that helps explain the independent versus the dependent samples. So we see that if we're just taking samples from two different populations and they have no relationship with each other, we call them independent samples. And if we take two samples from two different populations, but we've paired the subjects or paired the study, like I said with the example with the sneaker, on the same subject but two different feet. Classify each pair of samples as independent or dependent. Now, I don't have this in slideshow mode, so we do see the answer, but let's run through it anyway. Let's say the sample 1 is the triglyceride levels of 70 patients. And sample 2 is the triglyceride levels of the same 70 patients after they take a particular drug for 6 months. This is definitely a dependent sample as we have the two samples and we're talking about the exact same patients. So that means that the study will be comparing patient A to patient A in order to really relieve ourselves of those confounding variables that life definitely has an effect on our subjects and a study with humans in general. Another example, sample one is the scores of 38 adult males on a psychological screening test for attention deficit hyperactivity disorder or ADHD. Sample two is the scores for 50 adult females on a psychological screening test for ADHD. These are independent samples. The men and the women are not linked in any type of way. They both were given the same screening test, but it wasn't paired like they were spouses or siblings or anything like that, and therefore they were independent samples. When observations are randomly selected from two independent populations or experimental units are randomly assigned to two different treatments, where the variation between the experimental units is small, the sampling design is called independent experimental design or completely randomized design. So everything is completely random and there's nothing that is paired or dependent. Another diagram for us to see that in order to compare two means from two different populations, the easiest way is to take a sample from each of the populations and calculate a sample mean, and then work with a hypothesis test that is designed to compare these two means to determine whether the difference is significant or whether they are approximately the same. So here's a little flow chart that would be very helpful for when you're trying to decide to use a Z or a T. So if both population standard deviations are known and we say yes, and then we also verify that we are looking at populations that are known to be normally distributed, or we have taken a sample size that is of at least 30, we would be using our Z-test statistic. Now we know if that the sample size is not very large, not bigger than 30, and nothing in the problem indicates that it was normally distributed, we just can't do the test. It's not valid. The data is very specific, and either you grab a large enough sample size or you know something about the population being normal in order for any hypothesis test to be valid. Now, if you don't know both population standard deviations, then you do know that the sample size is big enough or the population is known to be normally distributed. Then you have to ask yourself one more question when we are comparing it to two means is, are the population variances equal? If they are, we would use a t-test, specifically using degrees of freedom n+1, n1, which is the sample size of the first population, and n2, which they don't need to be the same, by the way, -2. But if we have populations and either we don't know or we do know the variances are not equal, then notice that the degrees of freedom are separated, where you would do n-1 for the first one and n-1 for the second sample and not group them together. Okay. So some properties, if both sample sizes are larger than 30, the sampling distribution of x bar 1 minus x bar 2 has approximately normal distribution, as well as the sampling distribution of the difference of the sample means is normally distributed if both samples come from populations that are normally distributed. We don't really need to worry so much about these formulas as we will be doing everything in Rguroo. The assumptions that we need to check off. So recall that we had to check to make sure that we met a couple of a checklist of assumptions. If you took stats 1 with me, you would have probably learned it in the perspective of a flow chart, because I would write out the flow chart and kind of walk you through what questions you need to ask yourself to determine what types of tests you would be running. But in stats 2, we're looking at even more of the assumptions that we kind of just assumed in stat 1. So we do need to identify that the samples are independent of one another. If they're not, that we'll learn in the second half of chapter 8 how to deal with dependent samples. You have to recognize that both samples are simple random samples, so they were properly sampled from their populations. The populations are either known to be normally distributed or you're grabbing sample sizes large enough. And the population standard deviations are known for this particular 8.1 section. Okay, so you have population 1 where there's some population mean and standard deviation. You take a sample size and you calculate a sample mean, and that would be true for both populations. Let's note that the difference between the population means represents the hypothesized difference between the population means and that the Z statistic follows the standard normal distribution. Let's take a look at some examples now. So a telecommunications analyst is interested in knowing if there is significant difference in the average service outage times between cable television subscribers and satellite television subscribers. So she randomly selects 50 cable subscribers and 50 satellite subscribers for this particular study. She gives each subscriber a survey and asks them to record the length of time of each service outage for a month. She summarizes the results of the survey and calculates the mean outage for each television service. And here are the results. So we have cable and satellite, where we have the sample size being 50 for each. And again, it's not necessary that the sample sizes have to be the same. Our average outage time in minutes for cable was 8.8 minutes and satellite was 9.5 minutes, where the standard deviation is known as 3 minutes for cable and 2 minutes for satellite. The first thing that we want to do is calculate a 95% confidence interval for the population mean. Recall, since we haven't talked about confidence intervals in a bit, that we are creating confidence intervals to give ourselves our best guess with some sort of confidence of what we would expect the mean population outage times for each one of these particular populations. Is there persuasive evidence for the analyst to conclude at a 0.05 alpha level that there is a difference between the mean service outage times when referencing cable and satellite? So first we're going to do a confidence interval, and then we're going to run a hypothesis test. So let's do the confidence interval first. So from the information given in the problem, we know the following statistics and parameters. Since both sample sizes are greater than 30, they're both at 50, we can invoke the central limit theorem and assume that these samples are normally distributed, at least approximately, and therefore allows us to run the test with the z-test statistic because these sample sizes are large enough and we know both population standard deviations. Again, checking our assumptions. Are the samples random and independent? Yes. There was randomly selected 50 cable users and randomly selected 50 satellite users, and there was no connection between the two samples. And we also know both standard deviations and the samples are large enough, and therefore we are going to use a z-test statistic. So now at this time, let me stop sharing the PowerPoint and let's jump over to Rguroo so that we can learn how to do this together. Rguroo screen. Here we go. Okay, so let me sign in. Okay, so we want to run a hypothesis test with two means. Actually, sorry, we're going to run a 95% confidence interval. So we're going to come over here to analytics and go to analysis, and we're going to select mean inference, but this time for 1 and 2 population. We don't have a data set, so we're going to leave that blank. Instead, we are going to have to enter the parameters and statistics ourselves. So if we come down here to the summary, this little box here where it says paired data, that's for dependent samples, which we will learn about in 8.3 and 8.4. So we don't want to check that box. So what we want to do is under here, we want to put a label for the first population, and let's label the first population cable. The sample mean was 8.8 minutes. The sample standard deviation was not calculated. We have a population standard deviation and a sample size of 50. The second population came from satellite. The sample mean was 9.5 minutes. The sample standard deviation was not calculated, but we know the population standard deviation was 2, and the sample size is 50. Now what we want to do is we want to head over here to the population 1 and 2 tab. Now it looks like what we've worked with before when we only had one population. Again, we could toggle between the confidence interval tab and the hypothesis tab. Right now we're focused on a 95%, which is the default for confidence levels. We know we need a z-test statistic. Our sigma is known, so we know that's why we're using a z-test statistic. Again, it's saying, hey, if it's paired, also known as dependent samples, don't forget to check this box. Ours are independent, coming from completely different populations. Our variances are unequal, which is already defaulted because it noticed that when I entered them. And let's hit our little eyeball. So here we can see that the lower limit of the confidence interval is negative 1.6994 minutes, and the upper level of this is 0.29939 minutes. So this is saying that the difference between the population average difference between the two means of the populations varies between almost -2 to +3. Okay, that's talking about the difference. So this looks a lot different than when we did a confidence interval for one data set, because then it was talking in terms of minutes. But here, this is still in terms of minutes, but it's talking about the average difference between those values. So now if I head back to the PowerPoint, we would see that the conclusion is thus the 95% confident, we are 95% confident that the true mean difference in service outage time between cable and satellite subscribers is between -1.7 and 0.3 minutes. Sorry, not I think I misspoke a little earlier and said to -2 to +3 minutes, but it was 0.3 of a minute, which is a very small window. Thus, the confidence interval includes 0. This indicates that the difference in average service outage time between cable and satellite subscribers is not statistically significant at the 0.05 level. But now let's set up a hypothesis test to verify that conclusion that we made with a confidence interval. So the null hypothesis will always be set to the fact that there's no difference in the average outage time. And so no difference when you're subtracting would mean that the subtraction is equal to 0. And the alternative hypothesis will always be that there is a difference. So it's very typical that the alternative hypothesis is a not equal to sign. It's something other than 0. Okay, so mu1 is the true mean for the outage times for cable, and mu2 is set to be the outage times mean service outage times for the satellite subscribers, which is good because that follows along with how we labeled it in Rguroo. We labeled cable as population 1 and satellites as population 2. So that will be nice that the PowerPoint is labeling the same. The analyst is interested in whether or not there is a difference in the average service outage times between cable and satellite. Thus, the alternative hypothesis is two-sided, and it is a two-tailed test, as I previously stated. Since the analyst is interested in comparing the two population means, a natural way to make this comparison is to look at the difference between the two population means. Hence, the null and the alternative hypothesis are formulated as follows. So our null hypothesis is mu1 minus mu2 is equal to 0, indicating that the difference between the means is nothing. And the alternative hypothesis, mu1 minus mu2, is set not equal to 0, which indicates that the difference between the two means is something significant. Okay, so if we get a negative answer like we saw with the confidence intervals, all that negative means is that mu2 was larger than mu1. So if you're thinking, how can we talk about a negative difference in time? It really just means that the bigger mean was put second in the equation. In this situation, the hypothesized difference in the average outage time is 0. However, it is possible to be interested in non-zero differences, like I just stated. For example, if the analyst has been interested in the testing, if the difference in average service times was 1 minute, the hypothesized difference would have been set equal to 1. So specifying the significance level for this problem, we'll stick with the 0.05. Validate the assumptions of the hypothesis test, which we've already done because they are the same assumptions that we already verified for the confidence interval. So now let's head back to Rguroo and take a look at what it would look like to do a hypothesis test. So I can just come back to basics here from the same screen where I was doing the confidence interval because the values are already put in here for me. And then I'll go to test of hypothesis. The significance level is 0.05. The alternative hypothesis is a not equal to sign to 0. We are using a z-test statistic and our variances are unequal. So we result in, you can see here it says the alternative hypothesis is that the mean difference of cable minus satellite is not equal to 0. We have a p-value that is 0.16981. That is much larger than the set significance level at 0.05. Therefore, we're concluding that the test is not significant and we would fail to reject the null hypothesis. As a visual, we would see that here in the red is our p-value area, and that is set by the test statistic. Okay. So let's head back to the PowerPoint to see that conclusion written out and move on to the next example. So here, they're walking you through of how you would do it if you were to do it out by hand, which I don't recommend. Use Rguroo, much quicker. The calculated value of the test statistic does not fall in the rejection region because negative 1.373 falls between the critical values that are set. Now I looked at the p-value, which is the same p-value here, but remember there are two ways to solve a hypothesis test, through the critical regions or through the p-value analysis. There is insufficient evidence to conclude that the difference between the observed value and the hypothesized value is due to anything other than ordinary sampling variation. Thus, we fail to reject the null hypothesis with a significance level at 0.05. So there is not sufficient evidence at a 0.05 level to conclude that the average service outage time between the cable and the satellite subscribers is significantly different. Let's look at another example. So an elementary school teacher is interested in knowing if fifth grade girls take longer to read a passage from a book than fifth grade boys. She randomly selects 40 fifth grade boys and 40 fifth grade girls for the study. She gives each student several pages of the same book to read. The time it takes each group to complete the reading is recorded in minutes, and the results are as follows. So we have girls, there's 40 of them, and the average time it took them to read the passage was 11 with a standard deviation of 2. And the 40 boys took an average of 10 minutes to read the same passage, but with a standard deviation of 3. Is there persuasive evidence for the teacher to conclude at an alpha level of 0.05 that the fifth grade girls have longer reading times than the fifth grade boys. So remember, when we are setting up our hypothesis, we have to translate the claim. So here we are curious about a one-sided test. We're curious if the girls are longer. We don't apparently particularly care if the girls are on average taking less time. So that will affect what we do to set up this test. The null hypothesis is still going to represent that there's no difference in the average reading times between the girls and the boys, while the alternative hypothesis will indicate that the average reading time of the fifth grade girls is longer than that of the boys. We'll let the first population be the girls and the second population be the boys. So here we would set up the null and the alternative, that the difference between the average reading times is nothing, meaning that they are the same. And the difference between the average reading times, notice that we're saying the girls minus the boys is a positive number, meaning that the girls must have been bigger. So you have to be a little bit more thoughtful when you set up the alternative hypothesis, because you do want to make sure that if you're saying that the result of the subtraction is positive, that means what you are trying to claim is bigger, or in this case longer, is the first one in the subtraction. Validating our assumptions, are these samples independent of each other? Yes, the boys and the girls have no relation besides the fact they're both in fifth grade. Okay, the sample sizes, are they larger than 30? They took sample sizes of 40, so we're good there. So we can assume the samples are approximately normal. And sigma 1 and sigma 2, the two population standard deviations are given, and therefore a z-test statistic can be used. Now let's head over to Rguroo to complete this hypothesis test. Okay, so I'm going to come back here to Analytics, Analysis, Mean Inference, two populations. Now I'm going to label my population 1 the girls and the population 2 the boys to keep consistent with the PowerPoint. The average time it took the girls to read the passage was 11 minutes. Average time it took the boys was 10 minutes. Population standard deviation for girls was 2, and it was 3 for the boys, and both of them were a sample size of 40 kids. We head over here to population 1 and 2. We head over to test the hypothesis. The alpha level is still 0.05, but this time the alternative is greater than 0, because we're trying to show that there's a significant difference between the girls' times being longer than the boys. Z-test statistic, unequal variances, eyeball. So now we can see that the p-value is 0.039, which is less than 0.05. So we are going to conclude that this test is significant. And we could also take a look at the upper critical value being 1.6449, and the z-test statistic is 1.75, which falls to the right of our upper limit and therefore also verifies our conclusion that we are rejecting the null hypothesis, and therefore concluding that it is significant to mention that the girls' reading times is longer than the boys. So notice that if you use Rguroo to the reports for any one of the project or case studies, that it's really important that instead of just uploading the report, and you guys have been really good at this, but to make sure that you also annotate the report, explain what the report is telling you. So finishing up, we reject the null hypothesis. The p-value is less than the alpha level, and therefore there is sufficient evidence to conclude the average reading time is significantly higher for fifth grade girls than fifth grade boys. Now let's discuss, and really we're revisiting this with sigma unknown. Our difference would be that we'd be using a t-test statistic and not a z. So we're still talking about samples that are independent. They're simply random sampled. That the population either is normally distributed or the sample sizes are large enough. But this time we will not be given the population standard deviations. We will only have the calculated sample standard deviations. So let's take a look at this example. For consumer product, the mean dollar sales per retail outlet last year in a random sample of 15 stores was $3,425 with a standard deviation of 200. So recall from stats 1 that we're talking about a sample, and then they list the mean and the standard deviation in the same sentence, which is how I can interpret that that's a sample standard deviation and not the population one. For a second product, the mean dollar sales per outlet in a random sample of 16 stores was $3,250 with a standard deviation of 175. The sales amounts per outlet are assumed to be approximately normally distributed for both products. Assume that the population variances are equal. Ooh, okay, so we're going to have to remember that statement because remember, that's a checkbox that we have to check off. And since we don't know the population standard deviations, this assumption is going to make a difference in our calculations. So you really have to pay attention to all the things in here. You need to label the first population, sample size of 15, mean, X bar, S, sample standard deviation. Second population or second sample, N is equal to 16. X bar is 3,250 with a sample S standard deviation of 175. Our approximately normally distributed allows us to not care that the sample sizes are really small and our population variances are approximately equal. Okay, so we are wanting to now calculate a confidence interval for the difference in average dollars between the two products. Checking our assumptions, the independent random samples, yes, we are assuming that anyway. The two samples are drawn from populations that are approximately normally distributed, that was stated. Our population standard deviations are unknown, but we're told, ooh, that's checked wrong. So this should be over here, and this box, which isn't moving, should be on the other side, or maybe I'll just do this. Known, unknown. There we go. Okay, and the population standard deviation is known as assumed to be equal, which was stated as well. So let's now take a look at what to do in Rguroo. Hold on. Sample 3. Okay, so let's share Rguroo now. Okay, so we're again in analytics, analysis, mean inference, two populations. This time our population 1, we're talking about retail sales, so I'll just call it Pop 1 and population 2, because I really didn't have much of a name for them. We have the sales on average is $34.25 for the first population. Second population was $32.50. Sample standard deviation for the first population is $200, and the sample standard deviation for the second is $175. The sample size for the first one is 15, while the sample size for the second one is 16. Heading over to population 1, 2, we're on the confidence interval tab. It's a 95% confidence interval. We are using a t-test statistic, and we are assuming that the variances are equal. Okay, so we can see that our lower limit for the confidence interval, and again, this is the difference. This is the confidence interval for the difference between the two means, is between $37 and $312. That is a huge interval if we think about it. Oh my goodness. And we're 95% confident that the difference between the two retail store sales is somewhere between $37 and $312. That does not include the zero, and therefore, if we were trying to show that the difference between the means are significant, because zero is not included in this confidence interval, we would be fairly inclined to say that there's a good chance that the mean difference is significantly different. Back to the PowerPoint. So we are 95% confident that the true mean difference in dollar sales between product one and product two is between $37.20 and $312.80. That is, on average, product one generates between $37.20 and $312.80 more dollars sales than product two. Okay, let's test a hypothesis now where the sigmas are unknown but equal. Okay, so the assumptions again is that the samples are independent, that they're random samples, the population is normally distributed or has a large enough sample size taken, and we're still assuming that the population variances are approximately equal, even though we are not given the standard deviations for the population. So, for example, a cancer researcher believes that there may be an increase in life expectancy of women diagnosed with terminal breast cancer if they attend group therapy to discuss their illness. He randomly selects 40 women with breast cancer. 20 of the women are randomly assigned to a group that attends a group therapy session 1 day per week. The other 20 women do not attend therapy and are designated as the control group. The life expectancy in number of years from diagnosis until death is measured for each of the women in the study. So we have women in therapy and the stats, and women not in therapy and their stats. And we actually are given the individual data sets as well. But since we have the summary statistics, we don't really need anything to do with this data set, as the summary stats are already calculated for us. Is there persuasive evidence for the researcher to conclude with a 0.05 alpha level that the average life expectancy from diagnosis until death is significantly longer for women who attend these therapy groups? So determining the hypothesis and the null hypothesis, the null and the alternative rather, the null would state that there's no difference in the average life expectancy from diagnosis until death with women with terminal breast cancer, whether or not they attend therapy. And the alternative is going to state that women who have been diagnosed with terminal breast cancer will live longer than those who do not attend therapy. So notice this is not a two-tailed test. This is a one-sided test, as we specifically are talking about one being bigger than the other. So we'll let the first population represent the women in therapy and the second population represent the women not in therapy. And therefore, when we set up the hypothesis test, we will be doing a right-tailed test, making sure that the first mean in the subtraction is the one of women in therapy, so that we could use a greater than sign and expect a positive number if it is significantly bigger. So this would be our setup. The null is the subtraction of the therapy minus non-therapy. There is no difference. Therapy minus non-therapy, there's a positive difference indicating that the women in therapy have a longer life expectancy. The sampling distribution provides essential information in assessing the rareness of the test statistic. 2 questions must be answered in order to use the test statistic from the previous example. Are the samples taken from populations with normal distributions? And are the variances approximately equal? So this is exactly why this example gives us the data sets so that we can test for normality, which is something new. We haven't done this yet. So let's head on over to Rguroo. Okay, so these data sets I've actually already put into my data input. Women, I believe that should be it. 8.2 women. Where did it go? There it is. Let me double click to double check what it looks like. Okay, again, before I do anything, I like to make sure that my data set is properly imported. The labels are in the gray and all the data values are in the white cells. Okay, so I have women in therapy, women not in therapy data set just copied right from the PowerPoint. I could have created it right here in Rguroo, or I could have copied and pasted it into an Excel file and then uploaded it. Either way, it looks good. So now I'm going to head over to analytics and to analysis, mean inference, two populations. I'm going to import the data set, 8.2 women. Select the first variable. The first population will be defined as women in therapy. Notice the values automatically get calculated for us when we have a data set. And I'll identify that the second population will be the women not in therapy. And again, their values also get calculated. So we can see that the mean, sample mean is 1.96. It was summarized to 2 in the PowerPoint. And the sample mean is exactly 3.765, which was rounded to 3.8 in the PowerPoint. The sample standard deviation was rounded to 0.6 and rounded to 0.5 in the PowerPoint, but it shows that that is accurate. These are not paired. Okay, so the women they all have terminal cancer, but they were not paired off in any way. If we head over to population 1, 2, and to the hypothesis test we're trying to run, it's a 0.05 significance level. The difference between the alternative is greater than 0. We're trying to show that the women in therapy will live longer. It's not a z-test statistic because these sigmas are not known, and the sample sizes are 20. Now, right at this moment, we were not told that the population was normally distributed, nor do we have a large enough sample size. So at this time, we are unsure if this hypothesis test is even doable, as we don't know enough about the samples and the populations in order to determine whether this is valid or not. So up here, we have a normality test, a test for normality, and a normal probability plot. So let's select those because we only can select those when we have a data set, by the way, because it needs the data in order to test that stuff. And we also need to select equal variance and the test for equal variance, because we think that they're equal, but at least we hope that they're equal so we can run this test. But this test will tell us. So let's hit our eyeball and let's walk through some of the results in this particular test here. So here's the test of the hypothesis, but before we can determine whether this is even an accurate depiction, we need to take a look at the other things that we selected. So if we come down here for the test for normality, okay, it says here, null hypothesis, we're assuming the data is normally distributed. And we can see with our women in our p-values are very large, 0.5 and 0.96. So that indicates to us that yes, we would fail to reject the null hypothesis that the data is normally distributed. So that's how you read the test for normality. Large p-values, bigger than your significance level, fail to reject, data is normally distributed. Small p-values in this particular test would indicate we failed to reject the null, and that would mean that your population was not coming from a normally distributed. Okay, again, we've talked about normality plots, probability plots, and we're looking for them to follow a linear line, and we see that in that plot and in this one. Okay, so testing for the equality of the variance, the alternative hypothesis states that women in therapy is not equal to the women not in therapy. We have a large p-value here, which would tell us to fail to reject the null, which would state that the variances are equal. And therefore, we would say, okay, yes, the variances are equal based on this p-value. The population that this stuff comes from is approximately normal. So then that brings us up to the very top where we can now read our hypothesis test and know that there's validity behind it. And we see that the p-value, this again is scientific notation. This means times 10 raised to the negative 13 power. So that would mean to take this decimal point and move it 13 places to the left, which is a really, really small p-value, really, really close to 0. So we will definitely be rejecting the null hypothesis, and we would be concluding that this test is significant that the women in therapy do have a significantly longer life expectancy than those of the women who are not in therapy. Okay, this concludes our lessons on 8.1 and 8.2, discussing the difference between means, hypothesis testing, and confidence intervals, specifically with independent samples.